from American College in Madurai, PhD from SSN Institution, Chennai. He is a great scholar, research, researcher who is specialized in the field of bulk crystal growth by solutions and melt techniques, single crystal for nonlinear optics, ferroelectric and thermoelectric applications. To his credit, he has received 24 projects worth more than 320 lakhs. As a great Himalaya achievement, he has received 30 international and national awards. Some of the awards are Sri P.K. Das Memorial Best Young Faculty Awards in the year of 2022 from Nehru Group of Institution. Sri Sasi Ram Young Scientist Award in the 2022 from St. Peter's Institution. Asian Scientist Ranking in the year of 2022. Young Scientist Award in the year of 2021 from Tamil Nadu Academic of Science. Indian Spectroscopic Association ISPA Award for Spectroscopic in the year of 2019. SSN Best Faculty Researchers Award in the year of 2019. For SSN institution, his instruction international conference papers are 279. The followings are the milestone, the achievement of him. The 6 full-time PhD scholars have completed, 5 full-time PhD scholars are currently working, 14 PDF have completed, 5 JRF have completed, 2 scholars are currently working as a SSN JRF. He has produced uncountable PhD, PDF, and JRF scholars. Even a biographic can be written and his achievement due to time limitations. I restrict with a few achievements of him. With due respect, I invite Professor Dr. Muthu Sendil Pandian to take over the section. Thank you, sir.
Thank you, Dr. Cholan, for your nice introduction. Shall I start, Cholan?
Yes, sir. Yes, sir.
Very good afternoon. First of all, I would like to thank the convener of this conference, Dr. Dinesh Kumar, and the coordinator, Dr. Devi, HOD, and the organizing secretaries, Dr. Cholan and Dr. Manivannan, and other faculty colleagues of this Department of Physics, Gonzaga College, for giving me this wonderful opportunity to share some of my recent research work in unidirectional crystal growth for nonlinear optical and ferroelectric applications. I'm just sharing my PPT. This is the title of my today's lecture: Development of Device Quality, Nonlinear Optical and Ferroelectric Single Crystals for Practical Device Application. I myself, Muthu Sendil Pandian, working with Professor P. Ramasamy from SSN Institution, Chennai. So, growth of high quality with higher physical properties, in the sense higher optical transmittance, higher mechanical stability, higher electrical permeability, with the higher crystalline perfection, is still very challenging task for crystal growers by Solson growth method. High quality single crystals is of great importance when it comes to the device making. In this lecture, I am going to present you a method which gives you the crystals of very high quality, exceptional quality. So all the crystals, whatever you are seeing in my slides, are grown by 4 different Solson growth method, namely slow evaporation Solson growth method, slow evaporation Solson growth method, and then unidirectional Sankaraya Ramasamy method, In order to improve the crystalline quality with the higher physical properties, we have modified several things in unidirectional method. It is called as a RSR and ISR method, rotational Sanganaya Ramasamy method, and immersible ample SR method. So this is the outline of my today's lecture, introduction and what are the importance of the single crystals. And we have selected a lot of organic single crystals by this SEST, slow operation solution growth method. And what are the disadvantage when we go for the crystals by this SEST method. And the same kind of the organic single crystals we have also tried in this unidirectional crystal growth method. And what are the advantages when we grow the crystal and how to avoid the problems in this SEST method in order to use this unidirectional method. And then we have compared the physical properties and the crystalline perfection between this SEST and SR method grown crystals. And we have also tried the imaging techniques for identifying the convection and the concentration field in SR method of the crystal growth. And we have also tried the TGS crystal. This is a very interesting material. The phase transition of this TGS is 49 degree. So below this 49, this material belongs to the ferroelectric nature. After this 49 degree, this TGS crystal belongs to the ferroelectric nature. So in order to, for the curiosity to grow the crystals, these TGS crystals, so we have also tried to grow the crystals between the ferroelectric phase and also ferroelectric phase. We compared the physical properties and the crystalline perfection, and we have concluded what is the phase transition used for the practical IR detector application. And we have modified several things in SR method, and we have rotated the complete experimenter setup. It is RSR method, and we have also tried to avoid the impurity segregation in this SR method. It is called as a immersible ample Sanganaya Ramasamy method, ISR method. And we have successfully fabricated the type 1 type 2 SKG element from the grown crystal. And finally, we compare the physical properties and the crystalline perfection of this SR, RSR and ISR method grown crystal. And finally, I conclude my lecture. So single crystals forms an indispensable part of rapidly advancing technology. The art of growing these kind of single crystals has turned into science with a variety of wide range of application. And a variety of these kind of single crystals has been used in the lasers, nonlinear optics, LED, pyroelectric, piezoelectric detectors, optical components, and so on. So the availability of these kind of single crystals is equal to the ability to rise the country's economy. The ability to grow the crystal, this kind of single crystal, is an essential criteria for the competitiveness of our nation. So all these crystals are grown by the SR method for nonlinear optical and ferroelectric applications. And then you are going to see some of the practical device application of this grown crystal. We all know that quartz crystal is used in watches, and these are some of the possible lithium niobate single crystal application. This has been used in a piezoelectric gas lighter, optical data storage technology, telecommunication industry, and eye treatment through laser. And these are some of the application of the piezoelectric materials. They has been used in a medical ultrasonic transducer and underwater transducer to detect the tsunami, etc. And these are some of the borate family single crystals, and this has been used in a frequency conversion devices, and it also produces the lasers. So crystals can be grown from solution, melt, and wafer technique, in which solution and melt techniques are most commonly used for practical device application. These are some of the invention of several crystal growth methods from 18th century: hydrothermal method, Verneuil, Zekralski, Bridgman, and gel growth. And there are a lot of methods are available to grow the technologically important single crystals for practical utilization. And in this present lecture, I am mainly concentrated on this unidirectional
என்ன பண்ணணுமா இதுல
unidirectional solution crystallization method.
என்னென்னமோ இருக்கு அதுல எனக்கு கோவமா வந்தது நான் என்னென்னவோ போட்டு அனுப்பிச்சிட்டேன்.
So far, by this method, more than 200 numbers of crystals have been grown. We can able to grow the low soluble material, moderate soluble material, positive soluble, negative soluble. All kind of crystal can be grown by this Sanganaya Ramasamy method.
Next time.
And these are the classification of nonlinear optical single crystals. So one can able to grow the organic single crystals by this SR method. The problem in this SR method grown for in this organic single crystal is the SHG efficiency of this organic single crystal is very high comparable to this standard KDP, potassium dihydrogen phosphate single crystal. But the problem in this organic single crystal, due to weak van der Waals force, we cannot able to grow the large size single
மேம்
crystal.
அது பிடிஎஃப்ல தானே வருது நமக்கு. அப்புறம் எப்படி அது வேர்டா மாத்துனீங்களா?
For SHG application, so we can able to grow the inorganic single crystals by this SR method, but we cannot
இதுதானே
achieve the
போட்டிருக்கோம்.
highest.
நான்சென்ஸ்.
இல்ல மேம் ஆன் பண்றதுக்கு
We cannot grow the very highly efficient material in the inorganic category, but these are in order to get the advantages of this organic and inorganic. So now people are trying to grow the crystals by this semi-ionic single crystals. Here in the semi-ionic, one can able to achieve the largest solution code crystal, and also the SHG efficiency of these crystals are very high comparable to this kind of solution code crystals. These are some of the properties needed for the nonlinear optical single crystals. So before we go for the crystal growth, characterization or application, one has to ensure the physical properties and the chemical properties of the ground crystal. So it should be high nonlinear optical coefficient. For laser application, one must know the laser diameter threshold value of the ground crystal. So it be high laser diameter threshold value, fast optical response time, wide transparency range in the range of UV visible and IR region, 200 to 1100 nanometer. For practical device application, one has to ensure the ground crystals are very high thermal stability. And if we go for the cut and polishing, one has to ensure the highly mechanical stable crystal for practical device utility. So it should be high mechanical stability and chemical stability. The ability to process into the crystal and the device fabrication should be very easy. These are some of the conventional method grown crystals, 2-amino 5-nitrosylpyridine derivative single crystals for SHG application, and supported by DST, SERB, Science and Engineering Research Board, Government of India. So you see, from this SEST in a beaker, crystallizer or petri dish, this kind of very small size crystal can be possible. So we cannot grow the large size single crystals because of this method itself having some problems like high dislocation content, many milky opaques, micro cracks kind of things are always appeared in these conventional method grown crystal. But the SHG efficiencies, harmonic generation efficiency of some of these crystals are more than 30 times that of the standard potassium dihydrogen phosphate KDP single crystal. These 2-amino 5-nitrosylpyridine zinc fluoride single crystals are more than 75 times greater than that of the standard potassium dihydrogen phosphate single crystal. But we cannot grow the large size single crystals because of this the SEST method. So in order to avoid this issue, we have tried the same crystal. You see, these are the crystals grown by conventional method. The same crystals only we have tried in this SR method. Here what we have done is we have mounted a seed crystal at the bottom of the glass ampoule, and we have poured the saturated solution inside the glass ampoule, and we optimize the temperature at the top and bottom portion. So when the solvent evaporates, the remaining solid particles are growing as a single crystals, and we can able to grow this much of large single crystals by this unidirectional method. These are the as grown 2-amino 5-nitrosylpyridine derivative single crystal, and these are the cut and polished wafers. So several attempts have been made to grow the crystals by this solution growth technique like slow operation method, slow cooling, seed rotation, Bridgman, Zekralski, float zone, zone melting, and flux core method. But all the reported methods are at elevated temperature that leads to thermal induced growth defects, and it also has complicated equipment and difficulty in growing large size single crystals in these several methods, and multi-step processes are also involved. These are some of the TP4N single crystals grown by the conventional method using methanol as a solvent, and this is the ammonium tartrate single crystals grown by this conventional method. These are the morphology. We also tried this crystal by this SR method, and these are some of the SEST conventional slow operation cell technique grown 4-nitrophenols derivative single crystals for nonlinear optical application supported by DIBRNS, Department of Atomic Energy. This is some of the conventional method grown triazole derivative single crystals grown by the conventional method. You see, the very small size crystal can be grown by this SCST method. For application point of view, you have to grow the large size unidirectional method grown crystal. And these are the conventional method grown nonlinear optical and ferroelectric single crystal like ammonium tartrate, AMT4N, diglycine barium chloride, sodium sulfate dihydrate, triglycine sulfate, TGS, and diglycine zinc chloride single crystals for SGC application. These are some of the disadvantages of this conventional method. Due to temperature instability, multinucleation will be formed in the conventional method grown crystal, and the microcracks are appeared in the grown crystal, and the milky opaques are also formed due to the temperature instability in the conventional method grown crystal. And we cannot grow the single and bulk size single crystals when we choose the SCST method. And this has been already reported that the dislocations have been originated from the Grosseter boundaries. Because of this kind of Grosseter and Grosseter boundaries, the dislocation density of these conventional method grown crystals are very high. This we have identified using EPD, HP density analysis. And we cannot grow the highly uniformity in the conventional method grown crystal. And due to temperature fluctuation, the several solvent inclusions are also trapped in the conventional method grown crystal that we have identified using HRXID measurement. Not only this kind of sulfamic acid and the TGS crystal, almost all the conventional method grown crystals are having this kind of issues like multinucleation, microcracks, milky opaques, high dislocation density, less uniformity, low angle grain boundaries, and the solvent inclusion kind of thing. And these are the conventional method grown AMP4 and single crystal. So if you focus any one single crystal, conventional method grown crystal, all the crystals are having different planes, facets, Grosseter and Grosseter boundaries. But for application point of view, phase matchable portion is only useful, and other portion will be cutted after cutting the phase matching angle. For devices like frequency doublers and optical parametric amplifiers, phase matching needs to be achieved. Otherwise, the conversion efficiency would be very low. So in this point of view, this Sanganaya Ramasamy method, SR method, has given the solution, and it is possible to grow the crystal along its phase matching direction. Along whatever direction you want, whether you want to grow the crystals along its A direction, B direction, C direction, phase matching direction. So whatever direction you want, and you can grow by this SR method. So this is the diglycine bearing dihydrate single crystals, and we have selected this C direction, dominant plane, and we have mounted here, and we have grown this much of large size single crystal. And this is the SLCDK, sodium sulfate dihydrate single crystals by conventional method. The same crystals we have grown by this SR method, and this is the cut and polished wafers. This is the as grown this diglycine bearing dihydrate single crystal. And this is the morphology of this KDP, potassium dihydrogen phosphate single crystal. The phase matching direction of this KDP is 59 degree. So here what we have done is we have cut the crystal along its 59 degree and make it a very thin plate like a seed crystal, and we have mounted at the bottom of the glass sample. Then we have poured the saturated solution inside this glass sample. We applied the temperature at top and bottom portion, and we have successfully grown this SKG oriented KDP single crystals for laser application. And this is the SKG oriented crystal grown in RRK into the same SKG oriented KDP single crystals grown in our laboratory SSN. So this is this 2AP4N, 4-nitrofluoride derivative single crystal grown by the SCST. In a beaker, we have successfully grown this much of crystals by using SCST method for nonlinear optical application. The same crystal we have selected along its C direction, 001 direction, and we have mounted the seed crystal here, and we have successfully grown this much of large size single crystals by this SR method, Sanganaya Ramasamy method. The problem in this SR Sanganaya Ramasamy method is when we have used a lot of recrystallization process, and we have poured the saturated solution, and we have grown the crystal, but still there are a lot of impurities are appeared in this solution. So we cannot avoid in this solution grown crystal. So when we grow the crystal by this SR method, the impurities are pushed from this glass sample. At a particular time, we cannot control the impurity segregation. So once it achieves the more than one, then the crystal will be stopped growing. The multinucleation, milky opaque kind of things will be formed at the top of this SR glass sample. So in order to avoid this issue in SR method, so we have made several slats, which means the holes on this SR glass sample. We have completely rotated this RSR SR method with the solution, seed crystal, everything we have rotated. So when we rotate this solution with crystal, the impurities are pushed out from this SR glass sample. So comparable to this SR method grown crystal, one can able to avoid or minimize these impurity segregation in this RSR method grown crystal. So naturally, the physical properties of these RSR method grown crystals are very high comparable to this SR and conventional method grown crystal. We have also checked the crystalline perfection using HR measurement. The single and sharp peak we have achieved in this RSR method comparable to this SR and SCST method. So this is the ACRT method grown the same 2AP for N4 nitrogen derivative single crystal, and we have successfully fabricated the type 1 type 2 SH element here. This is the TGS single crystals for iodinator application. As I told you, here we can able to use this 010 polar B direction for this ferrovoltaic application. So other portion will be cutted after cutting this polar B direction. We cannot able to use. So again, we have to grow the crystal by this conventional method, and we have mounted the seed crystal in the SR method, and we have to grow the crystal along its polar B direction, and we have reported in journal. This is the glycine phosphate. We have grown the crystal along its polar B direction, and we have successfully grown the crystal by this SR method. So the crystal growth technique for the present investigation, I mainly focus on this SR method and then this SCST method. So before we choose the seed crystal and the material, we have to carefully optimize all these parameters, that is the instrumentation, synthesis and conventional crystal growth, and the selection of different seed crystal direction, whether we want to grow the A, B, C direction, or if it is a non-centrosymmetric material, and we have to select the phase matching direction. If it is a ferrovoltaic material, we have to go for the polar B direction. And different sizes of the glass sample, it depends upon the solubility of the material and the unidirectional crystal growth. And growth optimization means we have to maintain the two different temperature. One is at top portion and the bottom portion. So like 35, what's the growth rate? 36, 37, 38, 39, 40. So up to 40, one can able to grow the crystal by this solution growth SR method. Otherwise, after this 41, 42, this is the very high temperature. So the solvent evaporation rate will be very high. We cannot able to grow the good quality single crystal in this SR method. So 40, 39, 30 will be all right for all the solution growth crystal. And finally, growth rate measurement. This growth rate, it depends upon the what is the size, ID and OD, inner diameter and outer diameter, at top and bottom portion of this glass sample. What is the solubility of the material? What is the temperature you have selected at top and bottom portion? So it's all depends upon all these parameters. So the experimental setup of this SR method consists of the glass sample, and this SR glass sample is kept inside this water bath, and a small thin plate like a seed crystal is mounted at the bottom of the glass sample, and then we have to pour the saturated solution inside this glass sample, and a small hole was made on the top of the glass sample for solvent evaporation. And after few hours, due to gravity driven concentration, all the solid molecules are approaching the crystal surface directly. So the crystal surface attracts more atoms very easily. So because of the gravity driven concentration, at bottom portion near the seed crystal interface, crystal and solution interface, the concentration is high comparable to the top portion. And then we have to apply the temperature at the bottom and top portion. This top of this temperature is only for solvent evaporation, and this bottom of this temperature is for growing the crystals. So the only thing is we have to maintain the uniform temperature in between these seed crystal and the solution interface. If we cannot maintain the uniform temperature, then easily the multinucleation will be formed because of the temperature influctuation. Solvent inclusion will be formed in the grown crystal, milky opaques, microcracks, and all kind of dislocation issues will be happening in these SR method grown crystals. And to avoid the temperature fluctuation of the daily variation, water is frequently added inside this water bath. So we have to maintain the uniform this level to maintain the uniform temperature. So to freshly prepared saturated solution is frequently added inside this SR glass sample in order to avoid the fungus formation in the grown crystal. So after few weeks or few months time, depends upon the solubility of the material and depends upon the temperature what you have selected for this material, the crystal will be grown like this. So this is the diglazine barium chloride single crystals grown by this SR method. So this is the complete schematic diagram animation figure of this experimental setup of this SR method. So all the crystals we have grown based on this situation only. So this is the selection of seed crystal cutting and mounting. This is the TGS seed crystal. So using the morphological measurement, single crystal X-ray diffraction morphological measurement, you have to identify the direction or phase of this grown crystal. So this is the polar B direction, 0, 1, 0 direction. So using fine axa and blade, we have to cut the crystal like this, and we have to make a very small thin plate like a seed crystal, and we have to mount at the bottom of this glass ampoule, and then we have to pour the saturation solution. So this is a schematic view of this TGS seed crystal cutting and mounting. This is the actual TGS seed crystal is growing inside this glass ampoule, inside the solution along its polar B direction. You can see very easily. This is the polar B direction, and we have mounted. This is the transparent TGS crystal is growing along its polar B direction. This is the saturated solution of TGS, and this is the water bath. Now we are going to see some of the advantages of this unidirectional method. So the single crystal with specific orientation in a glass ampoule. So we can able to grow. So you see, this is the TGS, triglycine sulfate single crystal for photovoltaic application. So this is the C direction, dominant plane. So this is the A direction, this is the B direction. So you see, this is the C directed TGS, this is the B directed TGS, this is the A directed TGS. So whatever direction you want, you can grow by this method. Easily we can find out the growth rate along any plane. This is the lysine monohydrochloride dihydrated single crystal grown by SR method. So if you wish to identify the growth rate along different direction, so what you have to do is you have to cut the crystal under identical condition, under identical seed crystal thickness, under identical glass ampoule inner diameter and outer diameter, under identical saturated solution, identical temperature at top portion and bottom portion. You have to measure the growth rate along different plane for any case. So 100% crystal to solution to crystal convertibility is possible in this SR method. So the entire quantity of the solution is converted into the crystal. You see the seed crystal is mounted here along its polar B direction. The crystal is started growing here and it end here. The total length of the grown crystal is around 20 centimeter. You see there is no micro cracks and milky opaques kind of things in the SR method grown crystal. So with a thin plate like a seed crystal, this much of large size crystal can be possible by this SR method. You see very thin plate, you can able to grow this much of nearly 9 centimeter longest and 2.5 centimeter diameter of this SSD single crystal for the SKG application. The scaling up was relatively very simple by this method, and he is Professor P. Ramasamy. He was my PhD supervisor. He is also the director and dean of this SSN institution, and he is holding these benzophenone on organic single crystals for SKG application. So in conventional method, normally the crystal will be grown like this. So from small nucleation, then micrometer, millimeter, then centimeter. So if suppose in conventional method, this is the phase matching direction. You see, this is the phase matching direction for this practical device application. So this is the 1 day growth, and this is the 2 day growth, and this is the 3 day growth. This is the 4 day, this is the 5 day, this is 6, 7, 8. You see, there is no uniformity in the conventional method. There is no uniformity in the conventional method grown crystal. But in the case of SR method, it is the layer by layer growth, like this. So comparable to this conventional method, the uniformity of this SR method grown crystal is high. So it can be useful for the SKG application. So this is the sodium chlorobromoaxide single crystal along its A direction, reported by one Chinese laboratory, and he has also concluded that the uniformity of this SR method grown crystal is superior comparable to this conventional method grown crystal. So the requirement of large size crystal growth chamber is avoided in the conventional SR method grown crystal. So for growing the crystal by this SR method, if we wish to install in your UG, PG or PhD laboratory, you need only 5 to 6,000 rupees. So within this amount, one can able to construct all these small wire connection and glass ampoule setup. For growing the crystal by this SR method, you need only this 1 feet crust, 1 feet this water bath. This is nothing but this fish tank only, normal fish tank. And then you have to buy one glass sample, and you have to select the inner diameter and the outer diameter at top and bottom portion. It depends upon the, as I told you, the solubility and what is the material you have selected for this crystal growth. And then you need to have the 2 RTD temperature controller and 2 ammeter and 2 transformer. So one can easily construct this experimental setup in your laboratory. So this is the conventional method grown SSD single crystal. Along its C direction, we have successfully grown this much of large single crystal, and this is the cut and polished wafers. So not only cylindrical shape depends upon the shape of the crucible, any shape can be possible by this SR method. So the benzoate single crystal seed crystal is mounted here. So the large size benzoate can be grown by this method using xylene as a solvent. So this is the benzoate crystal organic material for SHG application, and professor is holding the organic benzoate single crystal. This much of large size seed crystal, single crystal is possible by this method. A thin layer of solution is in between the crystal and the glass sample, so there will be no mechanical stress into the grown crystal. So length to breadth ratio can be varied at with a stoichiometric solution. So this is the normal KDP single crystal, potassium dihydrogen phosphate single crystal grown by this conventional method. Normally the phase, plane and the growth direction would be like this. So but here in SR method depends upon the pH of the solution, one can able to increase or decrease of this growth direction of any crystal. So this is for the KDP crystal. If it is a new material, you have to optimize yourself with a different pH, with a different solvent, with a different material. This is a pencil shaped SR method grown KDP single crystals by this SR method. So crystals which have post-hoc cracking tendency can be grown without resulting the post-hoc cracking tendency because of the temperature instability in this conventional method grown crystal. There are a lot of micro cracks are appeared in the grown crystals in conventional method. But in the case of SR method, we have maintained the 2 different temperature, top and bottom portion. So there is a stable supersaturation in the grown crystal. There is a stable solvent evaporation, uniform growth rate. There is no chance in the formation of solvent inclusion in the SR method grown crystal. So this is the conventional method grown crystal with a lot of micro cracks and milky opaques. And the same crystal we have tried in the SR method, and we have successfully grown this much of large size transparent crystals. The crystal quality is always superior to the conventional method grown crystal. This we have confirmed with several characterization like UV with NIR, birefringence, optical transmittance, Vickers microharness, dielectric, HRXRD, HP density, and so on. So far by this method, more than this kind of 200 numbers of crystals have been grown. So we have successfully grown the positive soluble like this material and a negative soluble like lithium sulfate. You see the low soluble KAP, the 12.5 gram per 100 ml, and then moderate soluble 34 gram per 100 ml triclysine sulfate. You see the highly soluble material 265 gram per 100 ml. Benzoate using xylene as a solvent. So all these kind of crystals can be possible by this SR method. This is the low soluble KAP, and this is the moderate soluble TGS. This is the highly soluble benzoate single crystal. This is the negative soluble lithium sulfate single crystal. So based on our experience in this unidirectional method, and we have attempted to grow the world's longest solution crystal, and we have successfully grown this much of large size 1350 mm longest crystal with the 5.5 centimeter diameter of the grown crystal with the help of Professor G. Bhavanarana when he was the director of this National Physical Laboratory in New Delhi. In fact, we have initiated this growth run in 2008, and we have made several optimization in the growth run with a different temperature at top and bottom portion with a different solvent, with a different glass sample thickness. And in 2011, we have successfully grown this crystal, and we have made the cut and polished. We sent it for the characterization, and finally we published the result in MRP journal with the help of Professor G. Bhavanarana. Thanks to him. This is our actual 8 feet experimental setup of this SR method. The benzoate seed crystal is mounted here at the bottom of the glass sample, and we have maintained the one heating coil at the bottom of the glass sample and one heating coil at the top of this glass sample, and we have poured the saturated solution. When the crystal is growing from bottom to top, we have also increased the heating coil from bottom to top. So this much of transparent crystal can be grown by this SR method. This is the transparent benzoin single crystal grown by this SR method. This is a morphology of this benzophenone, and we have selected this 100 A direction for this longest growth because of the higher growth rate comparable to the other B and C axis. So this is a different growth stages of this benzophenone crystal. The seed crystal is mounted here, the roughness is started, then transparent portion is started here. You see the crystal is growing. This is the 850 longest benzophenone crystal. This is the 1350 longest benzophenone crystal grown by this SR method. This is the double refraction pattern of this benzophenone crystal. The total thickness of this crystal is 5.5 centimeter. Then we have grown lot of organic, inorganic, semi-organic, positive soluble, negative soluble single crystal by this SR method. And how to harvest the crystal from the glass sample. So this is the 20 centimeter longest TGS, triglycerin sulfate crystal along its polar B direction. So we have maintained one temperature at bottom portion and one temperature at top portion, higher temperature. It was 38 degrees Celsius. We cannot stop immediately, otherwise the multinucleation and microcracks will be formed in the ground crystal. And we have to reduce the temperature like 0.1 degree Celsius per hour or 0.5 degrees Celsius per day. Depends upon the solubility of the material. You have to select the cooling rate of this growth run. So we have to wait until it reaches the room temperature. So once it reaches the room temperature, and we have to kept out from this glass sample water bath. So this is the 20 centimeter longest TGS crystal inside the glass sample. Then using this diamond wheel cutter, we have to remove and you have to break the top and bottom portion separately like this. So this is the crystal inside the glass sample. Then using the diamond wheel cutter, glass cutter, you have to mark this top and bottom portion separately, very slowly, and you have to remove the glass sample using the sharp knife things. You have to very carefully remove, otherwise if you apply the stress, the microcracks will be formed in the ground crystal. So this is the 20 centimeter longest TGS crystal without having any microcracks and milky opaques kind of thing in the ground crystal. Then how to cut the crystal? So this is the 20 centimeter longest TGS crystal. So this is the diamond coated wheel cutter, and the ethylene glycol is kept inside this tray in order to avoid the formation of thermal stress in the ground crystal. This is a speed controller. So first, before we go for the crystal cutting, you have to identify the mechanical stability of your ground crystal, whether it is using Vickers Maker hardness measurement, whether it is a mechanically low, stable, or moderate hardening material, or very high hardening material. You have to confirm. Then you have to increase or decrease the speed of the diamond wheel cutter. So this is the cut portion of this TGS crystal. This is almost cut portion of this TGS crystal. And this is the as grown TGS. This is the cut portion of this TGS. So this is the 20 centimeter longest TGS crystal at its bottom portion, and this is the middle portion, and this is the top portion. Now we are going to see some of the SR method ground crystal, and this is the SSDH sodium sulfide diode single crystals for nonlinear optical application, and this is the cotton polished wafers, and this is the diglazing zinc chloride diode single crystals grown by this SR method, and this is the cotton polished wafers, and this is the 2-amino-phenoltryptamine derivative single crystals as grown crystal, and this is the cotton polished wafers. This is the ferroelectric glazing phosphate single crystals. This is the conversion method grown crystal. This is as grown crystal grown by SR method. This is the double refraction pattern. We have selected this polar B direction, and this is the cotton polished wafers of this glazing phosphate, and this is the 2-amino-phenoltryptamine single crystals grown by this SR method. And here normally in SR method, we evaporate the solvent and we grow the crystal, and this is the different kind of the crystal growth we have made, and we have successfully grown the crystal, and we have made the slow cooling run, and we have prepared the solution at 50 degrees Celsius. From 50 to 35 degrees Celsius, we have reduced the temperature, and we have successfully grown with the 0.02 degrees Celsius per hour of the cooling rate. And this is the KP, potassium dihydrogen phosphate single crystals grown by this SR method. And this is the ferroelectric TGS crystal along its C direction. And this is the cut-and polycid TGS crystal. And this is a sodium para-nitriphenol single crystals grown by this conventional method. And this is the grown by this SR method. And this is the cut-and polycid wafers. And this is the diglazine barium chloride monohydrate single crystals as grown crystal. And this is the cut-and polycid wafers. And this is the L-arginine 4-nitrophenolate 4-nitrophenol derivative single crystals grown by the SR method. This is ammonium tartrate single crystal as grown crystal with glass sample, and this is the without glass sample, and this is the cut and polish wafers. So we have grown lot of organic, inorganic, and semi-organic single crystals by two different methods, namely SCST, very small size crystal in a beaker or petri dish. We have successfully grown the same crystal, and we have selected for this SR method, and we have identified the phase or phase matching direction of the grown crystal, and we have mounted the seed crystal at the bottom of the glass sample, and we have successfully grown the large number of crystal by this SR method under identical condition, and we have characterized the physical properties and the crystalline perfection of the grown crystal. First, we have carried out the single crystal X-ray diffraction measurement in order to confirm the grown crystal, and in order to check the crystalline perfection of the grown crystals, and we have grown the high resolution X-ray diffraction measurement. And in order to identify the HP density of the grown crystal, we have selected this chemical etching. For laser application, one must know the laser diameter threshold value of the grown crystal, and the single and multi-shaft laser diameter threshold measurement we have carried out in ISC Bangalore. In order to identify the mechanical stability of the grown crystal, and we have carried out the Vickers microharness measurement. For optical quality, UV NIR. For electrical measurement, dielectric permittivity, dielectric loss, and we have also carried out the photoconductivity measurement, dark and photocurrent measurement, in order to identify the uniformity of the grown crystals, and we have carried out the birefringence measurement. Just a few minutes. And this is the conventional method grown SSD single crystal, and this is the SR method grown SSD single crystal. Similarly, we have prepared the several crystals for characterization purpose to identify the physical properties and the crystalline perfection of the SCST and SR method grown crystal. So the samples were prepared with the identical thickness. The surface damage is affected by the energy absorbing defects such as stains, scratches, and polishing contaminants, which strongly influences the physical properties. Therefore, all the characterization measurements were repeated several times on the highly polished crystals, thus minimizing any surface defects. In order to confirm the reproducibility, all the characterizations were repeated, and there's more or less similar results have been observed for the SCST and SR method grown crystal. And this is the HRXID measurement of this SR method grown sulfamic acid single crystal, and this is for this conventional method grown sulfamic acid single crystal. You see, there are lot of low angle grain boundaries are appeared because of the solvent infusions. So the entrapment of solvent molecules into the crystalline matrix is only responsible for the appearing these kind of low angle grain boundaries in the conventional method. But in the case of SR method, we have maintained the uniform temperature at top and bottom portion. So stable supersaturation, uniform solvent evaporation rate. There is no chance in the formation of solvent inclusion in the SR method grown crystal. So there is a single and sharp peak, which clearly indicates that the grown crystals are very high quality comparable to this conventional method grown crystal. And this is for this SSD gas, that golden color crystal. This is the crystal grown by the SR method. This is the crystal grown by the conventional method. Because of the solvent infusion, there are a lot of low angle grain boundaries that appeared in the grown crystal. The etching is the important and powerful tool to identify the crystalline perfection of the grown crystal. And we have performed the chemical etching for the several materials, and this is for the diglazine zinc chloride aggregated single crystal, and this is 5 seconds, and this is 10 seconds for the conventional method, and this is for the SR method. The approximate HP density of this conventional method grown crystal is 5.2 in 10 power 2 centimeter per minus 2, but in the case of SR method, it is less comparable to this conventional method. And this is the sodium sulfide diode single crystal. You see the HP density EPD of this conventional method grown crystal is very high comparable to this SR method grown crystal. And also on successive etching for the 5 to 10 seconds, this HP it's enlarged its size, retaining the geometrical shape and do not disappear, suggesting that the bits are due to the dislocation. You see the number of H bits in the conventional method grown crystal is high comparable to these SR method grown crystals. Randomly distributed but strictly oriented H bits have been seen in the case of conventional and SR method grown crystal. These are some of the various type of defects that appeared in the conventional method grown TGS, triglycerin sulfate single crystal. This is the solvent inclusion, and this is the low angle grain boundaries, and this is the micro cracks that appeared in the grown crystal, milky opaque, micro crystal. There are a lot of issues that happened in these conventional method grown crystal when we grow the crystal in a beaker or petri dish crystallizer kind of thing. Not only the TGS, almost all the silicon crystals are having this kind of issue. These are the various type of defects observed in the SCST method grown TGS crystal. You see, in the conventional method, there are a lot of growth band or growth sector boundaries, and dislocation have been originated from the growth sector boundaries. But in the case of SR method grown crystal, it is a single and morphological defined facet. There is no growth sector boundaries or less growth sector boundary comparable to this conventional method grown crystal. So the HP density, dislocation density of this SR method grown crystal is less comparable to this conventional method grown crystal. Because of this less HP density and higher crystalline perfection, the physical properties of this SR method grown crystal is very high comparable to this conventional method grown crystal. To identify the Vickers mechanical stability of the grown crystals, we have carried out the Vickers microharness measurement. This blue color indicates for this SR method grown crystal, this red color indicates for the conventional method grown crystal. Because of the higher crystalline perfection, the HV, Vickers microharness number of this SR grown crystal is high comparable to this conventional method grown crystal. And this is again for the glazing phosphate. This blue color is for the SR method grown crystals. The higher mechanical stability of this SR method grown crystal is, which clearly indicates that the crystalline perfection of this crystal is high comparable to this conventional method grown crystal. You see, the number of cracks appeared in the indentation in the SR method grown crystal is very high comparable to this conventional method grown crystal because of the very high mechanically hard material in the case of SR method grown crystal. So this is the 20 centimeter largest TGS crystal, and this is for the bottom portion. We have carried with the Vickers microharness measurement. This is the middle portion. This is the top portion. You see the large number of microcracks are appeared in the indentation. So the less number of cracks in the conventional method grown crystal is the indenter lands on the surface of the crystal around it displayed smoothly is the reason for the less number of microcracks in the conventional method grown crystal. But the flow of material under the indenter cannot take place smoothly in the very hard material like SR method grown crystal. So the reason for lower mechanical stability in the conventional method grown crystal is the solvent inclusion, and a variety of parameters such as variation in supersaturation, minor fluctuation in temperature, non-uniform growth rates are govern the solvent inclusion. This is the KCl, potassium chloride single crystal solvent inclusion pattern. This is the NaCl, sodium chloride solvent inclusion pattern. These are some of the solvent inclusion patterns appeared in our conventional method grown crystal. But in the case of SR method, as I told you, we have maintained the uniform temperature. There is no possibility in the formation of solvent inclusion in the SR method grown crystal. And in conventional method, the growth is mainly due to the diffusion process. So the availability of material ingredients are less in the conventional method grown crystal. But in the case of SR method, due to gravity driven concentration, the concentration at bottom portion is high comparable to the top portion. The crystal is growing here like this. So this is the conventional method grown crystal. This is the SR method grown TGS crystal. And single and multi-shot laser diamond threshold have been performed for this conventional and SR method grown crystal. And this is the SSGDH crystal grown by the SR method, conventional method. You see the laser diamond threshold value of this conventional grown crystal is 12 millijoule per centimeter square. But in the case of the conventional SR grown crystal is 17 millijoule because of the no solvent inclusion and a high mechanically stable material. And this is for the benzovenine crystal. You see 15 millijoule per centimeter square for this conventional grown crystal. But in the case of SR grown crystals, it is a 19 millijoule per centimeter square because of the higher crystalline perfection. And the dielectric tensor and dielectric constant and dielectric loss values have been measured for the conventional and SR method grown crystal. And this is the gold coated TGS sample, and we have carried out in an RRK Tindu. And the dielectric permittivity of the crystalline materials are the second rank tensor. For orthorhombic crystals, there are 3 independent components. For monoclinic crystal, there are 4 independent components. So this is the SR method grown SSD single crystals. So normally in crystal growth point of view, they grow the crystal, they identify the dominant plane, and they measure the dielectric constant and dielectric loss value of the dominant plane. But in the case of SR method, here what we have done is we have select the crystal along its A, B, C direction, and we have cut the crystal for the dielectric measurement. And anisotropic in the dielectric behavior were observed in the SR method grown crystal, and this blue color indicates for this A axis, and red color indicates for the B axis, and this green color for the C axis. And the higher dielectric permittivity and the lower dielectric loss, which clearly indicates that there is no solvent inclusion and higher crystalline perfection of this SR method grown crystal. And this is that TGS crystal to 49 degree. This is the phase matching transition temperature. So below this temperature, this crystal belongs to the ferroelectric nature. After this temperature, the crystal belongs to the paraelectric nature. So when the temperature increases, the dielectric permittivity also increases, and having maximum dielectric permittivity at 49 degree. So this blue color indicates for this SR method grown TGS crystal, 64.2 dielectric permittivity for the SR method grown crystal. But in the case of conventional grown crystal, it is 49.5 only. So the higher dielectric permittivity and the lower dielectric loss. So the optical quality of the grown crystal is identified using this UV with NIR measurement. So this is the transparent conventional method grown. This is diglazine barium chloride monohydrate single crystal. This is the SR method grown single crystal. You see, so these both are very transparent only, but the microscopic picture clearly seeing there are a lot of roughness is happened in this SCST method grown crystal because of the large number of dislocation density, HB density, more number of microcracks, milky opaque kind of thing in the SCST grown crystal. So, but in the case of SR method grown crystal, comparable to this SCST, less number of HB density, no solvent inclusion, microcracks. So the surface of this SR grown crystal is smooth, comparable to this conventional method grown crystal under identical optimization. So these are various type of defects observed in the SCST grown TGS crystal, and because of this issue, the transmittance of this conventional method grown crystal is less comparable to this SR method grown crystal. So 8% higher optical transmittance is appeared in this SR method grown glassine phosphate single crystal. You see in the case of SR grown crystal, because of the periodic arrangement of atoms, the output intensity of this grown crystal is high. But in the case of large number of optical scattering centers are appeared in the conventional method grown crystal. So there are large number of optical loss in the arrangement of atoms. The output intensity is low in the conventional method grown crystal. So low output intensity, which means the low optical transmittance in the conventional method grown crystal. High optical output, which means the high optical transmittance of the SR method grown crystal. And this is the birefringence measurement. See, the birefringence of this SR grown crystal is high because of the higher optical uniformity of this SR grown crystal. So we have grown several crystals, and we have characterized using the HRXID, UV vis NIR, dielectric permittivity, birefringence, and so on. In the case of crystal grown by this conventional method, because of the large number of Grosseteste boundaries, solvent inclusion, entrapment in the crystalline matrix, large number of scattering centers, microcracks, milky opaques, large dislocation density in the conventional method grown crystal, the physical properties and crystalline perfection of this SCST grown crystal is less comparable to this conventional SR method grown crystal. But in the case of SR method, what we have done is we have tried to avoid the Grosseteste boundaries in the grown crystal. So we can easily avoid the Grosseteste boundaries, or we can reduce the Grosseteste boundaries, and we have maintained the uniform temperature so that one can able to avoid the solvent inclusion, scattering centers, microcracks, milky opaques, and less dislocation density, which clearly indicates that the physical properties and the crystalline perfection of this SR grown crystal is high, superior comparable to the small size conventional method grown crystal. And this is the optical imaging of convection and concentration fields in the unidirectional growth. And this is the benzophenone we have selected for these imaging techniques along this 100 direction, A direction. Because of the high solubility material, we have selected this benzophenone. And this was done in RRK Tindu. We have performed the real-time and in-situ optical imaging of concentration and convection field during the unidirectional crystal growth of this high-soluble benzamide crystal. And the stratigraphic technique is used to visualize the convection to quantify the thickness of the solidal boundary layer and the crystal growth rate. The magnetointerferometry used to quantify the gravity-driven concentration profiles during the growth. So this is the actual experimenter setup we have done in RRK Tindur, and this is the complete experimenter setup. So we have performed the run between the 25 degrees Celsius to 23 degrees Celsius with 0.02 degrees Celsius per hour of cooling rate. So we have mounted the seed crystal and we have poured the benzamide solution. The roughness is started here and the transparent portion is started here. So our main intention is to focus the seed crystal and then the solution interface. So this is a scattergraphic images of this concentration field of this SR method grown benzamide crystal. You see the concentration at bottom portion is high comparable to this top portion. So this is for 1 day and this is for the next 5 days and this is for the next 5 days and this is for the next 5 days. So totally 16 days. At this 6th day, you see the plumes are started from the bottom of the glass ampoule. The plume is nothing but the movement of fluid flow from the high concentration to low concentration. If you focus any one plumes, you see the plumes are moving up, up. Then the plumes are disappearing. Then new plumes are started from the bottom of the glass ampoule. From this observation, one can able to conclude that the gravity-driven concentration is only responsible for the growth of the crystal in this SR method. And then this is the TGS, that triglycerin sulfate single crystal phase matching point at 49 degrees Celsius. So below this temperature, this is crystal belongs to ferroelectric phase. Above this TC, this crystal belongs to the ferroelectric phase, and we have successfully grown the crystal at its below and above TC. So this is the conventional growth, and this is the polar B direction. And we have selected 36 degrees Celsius at top portion, 28 at the bottom portion. This is the heating coil arrangement we have done in RRK Tindu. So this is the ferroelectric faceted grown crystal, and we have reported in 2021. And this is the above TC. We have maintained the temperature 54 degrees Celsius at top and bottom portion. And this is the parallelic faceted grown TGS crystal. And we have compared the physical properties, chemical properties, and the crystalline perfection of the grown crystal. You see the ferroelectric faceted 25 picocoulomb per Newton, but in the case of parallelic faceted 35 picocoulomb per Newton. And the higher optical transmitters in the ferroelectric faceted grown TGS crystal, and higher mechanical stability in the ferroelectric faceted grown crystal, and less HP density of this ferroelectric faceted grown crystal, which clearly indicates that for ferroelectric application, one can select this ferroelectric faceted grown TGS crystal along its polar B direction, comparable to this ferroelectric faceted grown crystal. And now we are going to see some of the modified SR glass ampoule. So when we select the ethanol, methanol kind of acetone kind of solvent, the multinucleation will be formed at the top of the SR glass ampoule like this. So in order to avoid this kind of multinucleations, we have introduced the glass bend kind of thing like this. So if the multinucleation will be formed, it falls only on the top of the glass ampoule. It will not fall on the near the crystal and the solution interface. And we have successfully grown the SR crystal like this in the modification. So this is the conventional method grown crystal, and this is the SR method grown crystal, and this is the cut and polycid wafers, and this is the point seed rotation experimental setup, and this is the 400 derivative single crystal, and we have grown along its C direction, and this is the Teflon sheet and rod. This is the seed crystal, and we are selected for the longest growth, and this is the 2-liter solution container, and this is the 5-liter solution container. And this is for the cooling rate of 0.1 degree Celsius initially, and then we have increased the cooling rate at 0.2 degree Celsius per day, then 0.5 degree Celsius per day. So when we go the above 0.5 degree Celsius, then multinucleation will be formed in the beaker. This is the actual 4-interval derivative single crystals grown in the ACRT method. This is the as-grown crystal. From this crystal, we have successfully fabricated the type 1, type 2 SKG element. So at that phase 1, phase 2 SKG element, the SKG efficiency will be high comparable to this normal grown crystal. So this is the 1-inch thickness of this 400 derivative single crystal, and we have fabricated the type 1, type 2 SKG element. And you see, this is some of the impurities incorporation in the SR method grown crystal. This is a 4 interpolated derivative single crystal. So in order to avoid this SR method grown crystal, we have introduced several slats on the SR method glass ampoule. Using this ACRT method, we have designed this RSR method. So this is the width slat and this is the width tube. The seed crystal is mounted here. The saturated solution is poured here. Fill up with all these container, and we have completely rotated this seed crystal. And this is the RSR method with the slat, and this is the RSR method with the tube. The seed crystal is mounted here. The crystal is growing, and this is the RSR method with the tube. This is the different growth stages of this RSR method with the slat. You see the transparent 400 derivative single crystal. Here one can able to avoid the impurity segregation. One can able to minimize the impurity segregation in this RSR method comparable to this SR method grown crystal. This is the RSR method with the tube, and this is the RSR method as grown crystal, and this is the cut and polish wafer. So this is that 4 interpolated derivative single crystals by this conventional method. In a crystallizer, we have successfully grown this crystal, and this is the crystal grown by this SR method, and this is the crystal grown by this RSR method. In order to identify the crystalline perfection of the grown crystal, so we have carried out the HRXRD, high resolution X-ray diffraction measurement, the 56.5 hour second for this conventional method growth, and 45.5 hour second, because here we have avoided the growth sector boundary, solvent inclusion, micro cracks in the SR method grown crystal. So comparable to this conventional method grown crystal, the SR method grown crystal is having higher crystalline perfection because of the no growth sector boundaries, no solvent inclusion, micro cracks, and milky opaque kind of things. But there are some impurities are appeared in the SR method grown crystal. In order to avoid this, we have modified this SR method. This it is a RSR method. So here we can able to minimize the impurity segregation in this RSR method. So you see the crystalline perfection of this RSR method grown crystal is 30 hours second, comparable to this SR and conventional grown crystal, it is very less. So this is comparison between the SR and RSR method optical transmittance. You see higher optical transmittance in the RSR method grown crystal comparable to this SR method grown crystal, and higher mechanical stability for the RSR comparable to this SR, and the higher laser damage threshold comparable to this conventional SR. So this is the immersible ample Sankaraya Ramasamy method. So here, so you don't want to disturb in this SR method. We have mounted the seed crystal here, and we have filled the solution up to this level, and we go for the high temperature to low temperature, and we have successfully grown this crystal by this RSR method. And this is the as grown crystal. This is the cut and polished wafers. In order to identify the crystalline perfection at top, middle, and bottom portion, we have carried out the HRXRD measurement. So the crystalline perfection of this ISR method grown crystal at top, middle, and bottom portion is more or less equal. So the final conclusion of my lecture is we have selected several organic, inorganic, and semi-random single crystal by this conventional method. More efficient material only we have selected for this growth, and the same material we have selected for this SR growth, and we have mounted the seed crystal, and we have successfully grown the crystal by this SR method. We have compared the physical properties and the crystalline perfection between these SCST and the SR method grown crystal. The SR method grown crystals are having higher physical properties comparable to this conventional method grown crystal, but still there are a lot of impurity segregation that happened in this SR method grown crystal. In order to avoid this issue, we have slightly modified this SR method. It is called as a RSR method, rotational Sankaraya Ramasamy method. There we can be able to minimize the impurity segregation in the RSR method grown crystal. So we have compared under identical condition, we have compared the physical properties and the crystalline perfection of this SR, conventional SR, and the RSR method grown crystal. The RSR method grown crystals are having higher physical properties and a higher crystalline perfection comparable to this conventional SR and the conventional slow operation crystal. So we can able to use this kind of ferroelectric crystals and nonlinear optical crystal for practical device application. So thank you very much for your kind attention. If you have any question, I am very happy to respond. Thank you. Thank you very much.
Thank you, sir. It is the time for questioning. I invite the participants to ask questions.
Hello, sir.
Yes, sir. Please tell me.
Sir, I have some questions regarding silicon wafers.
Silicon wafer. Okay.
Okay. I want to develop a silicon oxide on silicon wafer, sir, because
Okay.
it is right now it is currently used as anode for lithium-ion batteries rather than graphite. So, if there is any simple facial method to grow a silicon oxide on the silicon wafer?
In solution growth, you cannot try the silicon material, but in our laboratory, we have made several silicon material, silicon, single crystalline silicon and a multi-crystalline silicon using DS furnace. But in
Okay,
solution
sir.
growth method like
Okay.
SEST, SR, RSR, ISR, cannot try the silicon kind of materials. So you should have
Okay, sir.
the solvent for your material. So this is very simple step. You have
Okay.
to prepare the saturated solution and you have to pour the saturated solution. Once the solvent evaporated, the remaining solid particles are growing excessively pressure. This is the simple principle for the solution method. But your material you
Okay.
cannot able to dry in the solution method. You have to go for the uh, DS method, direction solidification method.
Okay, sir. Thank you, sir.
Thank you. Any other question from the participants?
Sir, I have one doubt.
Yes, please.
Sir, while seeing my papers, the HRXRD is marked with arc seconds as well as radian, which is a very good dimension
No,
for me.
normally HR extend unit is arc seconds only, sir.
Okay.
Arc second. Yes.
Thank you, sir.
Thank you.
Dear participants, you kindly ask the question, or else you can post the question in the chat box. Sir, one question is asked by Bharanidharan. What is the intensity of the UV visible NIR spectroscopy?
What is the
Intensity of the UV vis chat box.
so
He has asked the
intensity we don't consider. We just grow the crystal and we prepare the transparent single crystal for the UV NIR transmittance from UV visible IR region 200 to 1100 nanometer. We mount the seed crystal under identical SEST and SR method ground crystal. We get the optical transmittance. Our ultimate aim is to grow the highly optically transparent crystal. So we simply compare the crystals grown by SEST and SR, which is the highly optically transmitted crystal. And that crystal we go for the other applications.
Sir,
Yes, madam. Please tell me.
sir, the another question was also in the chat box, sir. Bharanidharan
Okay.
asked the question that
Okay.
how can we say it is high light transmission crystal?
How high light transmittance? 1 minute. I don't
I
say
think
anywhere it is a high light transmittance crystal. I don't understand the question, sir. Sorry.
in that case, the
Optically,
participant,
highly optically transmittance crystal. Yes.
I think in that case, Bharanidharan, you please contact the sir, or else you contact.
No, it is not a high light transmittance crystal. It is a highly optically transparent crystal. Yes.
Yes, sir. Thank you for your wonderful presentation, sir.
Thank you. Thank you very much, sir.
From the Gonzaga family, we would like to thank you for giving the wonderful presentation, and thank you for accepting our request and delivering the wonderful the crystal growth techniques which was implemented in SSN institution. Really, it was very much useful for the participant and as well as the students.
Thank you.
From
Thank
my
you.
bottom
Thank you,
of
Dinesh.
heart, I would like to thank you, sir. Thank you so much.
Thank you. Thank you very much, Dinesh. Thank you very much. Thank you.
Thank you very much, sir, for your presentation. Really, it was good and inspired. It will help us to grow in our further moves. Thank you, sir.
Thank you. Thank you, ma'am. Thank you very much.
We will send the feedback link in the chat box. Kindly, I request all the participants to fill the feedback from the form and submit it. Only participants, those who have submitted the feedback form, can eligible to receive the e-certificate. I repeat, only participants, those who have submitted the feedback form, can eligible to receive the e-certificate. Today, by this session, we conclude the webinar. We hope you have learned and got many ideas about this field. I would like to express our deepest appreciation to all of our wonderful presenters for their valuable contribution. I would like to thank all the participants for your valuable time and attention today. Kindly, I invite all the participants to come and join by using the same link on tomorrow at sharply 10 a.m. Thank you all.